Hi everyone. So today I'm going to share with you on the Proton NMR, nuclear magnetic resonance. So we are going to focus on how to interpret Proton NMR spectrum. So these are the four information that you can get from Proton NMR spectrum. We're going to look at the information, these four main point here, one by one. So first, I'll tell you what does number of signals show us, and how to read the chemical shift value for the signal, and what is the meaning of the integration, and what does the multiplicity or the spin-spin coupling of the signals tell us about the structure of the compound. So as what you can see here, okay, in I have this example here, okay, drawn by me. You can see there are three signals. Okay, there are three signals, one signal, two signals, and three signals. So these are the number of signals that later I'm going to share with you. Chemical shift value. Okay, so as you can see, the chemical shift value is in unit of ppm. So you can see the three signals here, they are having different ppm. Okay, they are having different chemical shift value. So for example, this first signal is with maybe around 1.6 ppm. Okay, so what does this number here show us? Okay, how we relate this number, this value with the structure of the compound. This one later we'll discuss. And the integration, okay, you can see there is a blue line. Okay, there is the blue line that overlap with the signal. So this is the integration. Later I will share with you on how to read this, and how we use this information when we trying to solve a structure of a compound. And for the spin-spin coupling, or in another terms, we say it is the multiplicity of the signal. Okay, as you can see here, here you have three signals, and they are splitting into different fine line. Okay, for example, this signal here, okay, is one signal, but it is splitted into two fine line. You can see two fine line here, 1, 2. Okay, and how about this signal? This signal is in only one single fine line, and this signal is splitted into three fine line. So this is the multiplicity. We'll further discuss about this later. So first, let's start with the first information that you can get from Proton NMR. Okay, now we are focusing on Proton NMR. The first one is the number of signal. Okay, the number of signals tell us about it is equal to the number of non-equivalent proton in the structure. So maybe I give you some example so that it's easier for you to understand. Let's look at this example. Okay, this structure, CH3, CH2, CH2, Br. So remember that now we are focusing on Proton NMR. Proton is hydrogen here, okay, and the signal on the Proton NMR, they are all given by proton. They are all given by hydrogen. Okay, so we are going to focus on proton, the hydrogen. Here in this structure, this CH3, CH2, CH2Br, you can see in total there are 7 proton. Okay, proton is hydrogen. Okay, proton is hydrogen. So they are in total 7 protons, but because some of the protons, they are equivalent, they are the same, they are going to give you one signal. So even though you have 7 proton here, you're not going to see 7 signal on the NMR spectrum. Okay, so in total, you only see 1, 2, and 3. In total, you're going to see 3 signals. because there are three non-equivalent proton. Okay, these three non-equivalent protons will give you three signals. So normally the hydrogen, okay, the hydrogen that attached to the same carbon they are equivalent. Okay, they are equivalent. So as you can see here, these three proton, they are the same, so they are equivalent. These two proton, they are equivalent, and these two proton, they are equivalent. So in total, you have three types of proton, three non-equivalent proton. Okay, so this for this structure, for this compound, you'll see three signals on NMR, on the proton NMR spectrum. Okay, we look at another example. I give you another structure. So now let's look at this structure. Okay, so for this structure, you can see this is an ether. It is a symmetry ether. Okay, you can see a plan of symmetry here. Okay. So just now you have seen that the proton that attach to the same carbon, they are normally equivalent. They give one signal. And also, if let's say you have a symmetry structure, okay, then some of the proton, they will also be equivalent. So for example, by looking at this structure, which is a symmetry molecule, okay, you know that they are the same. Okay, these three proton, they'll give you one signal, and these two proton give you another signal. But because this is a symmetry molecule, okay, this is a symmetry molecule, so you can see they are actually mirror image. So maybe I change the color so it's easier for you to read. Okay, so this three proton here is the same with these three protons. So in total, 6 protons, they are the same. They give you one signal. Okay, give you one signal here. And for this CH2 and CH2 here, okay, these two hydrogen and these two hydrogen, they are equivalent, so they give you another signal. So in total, in this structure, they are two non-equivalent protons. So you see two signals on the proton NMR spectrum. Let's move to the next example. Now maybe I give you an aromatic compound. Okay, so you have aromatic compound with two substituent here. Okay, you have OH. Okay, so if you look at this aromatic compound, it's actually something like this. You have X and Y. So remember that, okay, remember that here you have hydrogen, here you have hydrogen, okay, you have the aromatic proton. So actually, if you look at this structure, there is a plane of symmetry across the ring. So this hydrogen and this hydrogen, they are equivalent. They give you one signal. This hydrogen and this hydrogen, these two, they are the same. And you have one hydrogen here from OH. This will give you another signal. And you still have one more hydrogen here. Okay, these three hydrogen will be another give you another signal. So in total, for this structure, for this aromatic compound, you have 1, 2, 3, 4. You have 4 non non-equivalent proton. Okay, you have 4 types of protons. You have 4 non-equivalent protons. It'll give you 4 signal. Okay, I'll give you one last example. CH3, CH2, I give you an ester. Okay, CH2, CH3. Okay, this is an ester. It is not a symmetry compound. So the hydrogen at different carbon, they are different. So in total, you have 1, 2, 3, 4. All these 4 groups of proton, they are non-equivalent. Okay, because it is not a symmetry molecule like what you have seen in the ether, the example, the previous example. So in total, you have 4 non-equivalent protons. So you can see 4 signals on the proton NMR spectrum. So we have done with the first point, which is the number of signal. Now we move to the second point. Okay, the second point here is the chemical shift. Okay, the chemical shift value. The chemical shift is actually the position of the signal on the spectrum, like what you have seen just now. Okay, so you can see the signal, they are with a different chemical shift value, maybe 1 ppm. But for the for proton NMR, because now we are focusing on proton NMR. For proton NMR, the signal, they normally spread from 0 to around 10 ppm. Okay, sometimes you see some signal, they may be at 11 or maybe slightly more than 11 ppm. Okay, but this is the normal range of a chemical shift value that you can find for proton NMR. And this chemical shift value, okay, if the small chemical shift value or a great chemical shift value depends on the shielding and de-shielding effect. Okay, this is the one that we are going to see later. The shielding or de-shielding effect. Okay, this shielding or de-shielding effect will affect the chemical shift value. So generally the shielding effect, or you say the shielded proton, okay, the shielded, or you can say the shielded proton, okay, they will have lower chemical shift value. Okay, lower chemical shift value. For the de-shielding effect, or you say the de-shielded, okay, the de-shielded proton, they are with high chemical shift value. Okay, compared to the shielded proton, they are with higher chemical shift value. Okay, so just now you have seen that a spectrum looks like this. You have start from 0. Okay, start from 0, then normally, generally for proton NMR, you spread up to 10 ppm. Okay, this is ppm. So some signal, they may be appear here with low chemical shift value. Some signal, they may be appear here with high chemical shift value. Okay, so this, as I mentioned just now, this chemical shift value affected by the shielding or de-shielding effect. So now let's look at what is this shielding or de-shielding effect. So different types of proton depends on the structure of the compound. Okay, they have a different chemical shift value. So normally when we try to interpret the proton NMR, we will use a correlation table. So in the correlation table, you can see what is the type of the proton and the range of the chemical shift value that that proton should have. Okay, so now I'm going to share with you on what is this shielding and de-shielding effect. So to understand this, first you have to know the principle behind NMR. So as you know, okay, in NMR, nucleus is the one that interact with the radiation, the radio frequency. Okay, in NMR is the radio frequency, and nucleus is the one that interact with the radio frequency. Okay, a different with the spectroscopy methods that you have learned before, like IR, like UV spectroscopy. In those type of techniques, the one that interact with the radiation is the electron. Okay, but in NMR, nucleus is the one that interact with the radiation, with the electromagnetic radiation. And the electromagnetic radiation involved in NMR is radio wave frequency. Okay, is the radio wave. And nucleus is spin. Okay, so for it to spin also, you need to have external magnetic field. Okay, external magnetic field. So in the NMR instrument, you have a big magnet that supply the magnetic field. Okay, B is the magnetic field. So under strong magnetic field, the nucleus will spin faster. Okay, under weak magnetic field, the spinning of the nucleus will be slower. And you have to know that in a molecule, the nucleus of an atom is not naked. It is always surrounded by electron cloud. Okay, you'll be surrounded by electron cloud. So depending on the structure of the molecule, some nucleus, okay, now the nucleus that we are mentioning is actually the proton nucleus, okay, the hydrogen nucleus, the proton. So the nucleus, depending on the structure, some nucleus, they are surrounded by a very dense electron cloud. Okay, some nucleus, they are surrounded by not so dense, okay, less dense electron cloud. So this electron cloud will weaken the magnetic field, the strength of the magnetic field that we supply to the nucleus. Okay, so for example, if let's say now for these two nucleus, which one is with thick electron cloud, one is with thin electron cloud, if let's say they are with the same strength, they are supplied with the same strength of external magnetic field. Okay, this and this, they are the same. But the spinning of the nucleus depends on the effective magnetic field that experienced by the nucleus. Okay, the spinning of the spinning speed, the spinning frequency of the nucleus depending on the effective magnetic field. Okay, the effective magnetic field is the magnetic field that experienced or felt by the nucleus. Okay, the felt by nucleus. So for the one with thick electron cloud, the effective magnetic field will be lower because now the nucleus is said to be shielded. Okay, this is shielded. This nucleus is shielded by thick electron cloud, so the effective magnetic field is lower. Okay, when the effective magnetic field is lower, the precessional frequency also become lower. Okay, and the chemical shift value of the proton is also become lower. Okay, so when the nucleus is shielded by thick electron cloud, the effective magnetic field is now weaker or lower. Okay, the effective magnetic field, I repeat again, it is the magnetic field that experienced or felt by the nucleus, okay, by this nucleus. So because of the thick electron cloud, okay, very thick, so now it is shielded, the nucleus is said to be shielded, and the effective magnetic field is weaker, and this will cause the precessional frequency, the spinning frequency of the nucleus is now also lower, and this will lead to lower chemical shift value. Okay, and let's look at the one which is de-shielded. Okay, this nucleus is said to be de-shielded because of the thin electron cloud, okay, compared to this nucleus. So this nucleus is de-shielded, okay, or less shielded. The electron cloud is not so thick, so compare now we always compare, okay, compared to this nucleus is de-shielded, so the effective magnetic field is greater. It lead to higher precessional frequency and later lead to higher chemical shift value. So to summarize this, okay, this is the spectrum. Start from 0, maybe up to 10 ppm. The shielded, okay, here, the shielded proton will be with low chemical shift value. Okay, the de-shielded proton will be with higher chemical shift value. Okay, and here I would like to introduce another term to you, which is downfield and upfield. So for the proton which is with high chemical shift value, the de-shielded proton, it is also say to be downfield. Okay, the high chemical shift value proton, they are always described as to be downfield. Okay, so high ppm is downfield, and low ppm, okay, the chemical shift is in terms of ppm, the unit is ppm, so the low chemical shift proton is upfield. Okay, so there are several factors that will affect the de-shielding effect. Okay, they will cause the electron cloud around the nucleus to be thinner. So now let's look at the different factors. First is the electronegative atom. Okay, so there are some factors they will lead to de-shielding effect. Let's look at electronegative atoms or the electron withdrawing group. Let me give you some example. So let's look at this methanol. So as you can see here, this tree will give you one signal, and this proton is another signal. So you can see this alcohol OH group, this proton is just next to this electronegative oxygen. Okay, oxygen is an electronegative atom. So this electronegative atom will cause de-shielding effect. Okay, electronegative atom will attract the electron cloud. Okay, it will attract the electron cloud towards itself. So now this proton is de-shielded. De-shielded. Okay, this alcohol proton, OH proton is de-shielded. So compared to these three proton, okay, this proton is with higher chemical shift value. Okay, these three proton, they are going to give you one signal and they are with lower chemical shift value. Let's look at another example. Okay, another structure, CH3, CH2, CH2, NO2. Okay, this NO2, nitro is an electron withdrawing group. So we have three signal here, three non-equivalent, 1, 2, and 3. And the distance between the proton and the electron withdrawing group will also affect the de-shielding effect. So of course, the one which is nearer to the electron withdrawing group will have a greater de-shielding effect. So this proton is with greater de-shielding effect with compared to the other two, you're with the highest chemical shift value. Okay, and followed by this one. This one is with lower chemical shift value compared to this, okay, but higher compared to this. So it is in the middle, okay. And for this proton, it is the one among these three. It is furthest away from electron withdrawing group NO2. So it is with the lower chemical shift value. Okay, give you one more example on methyl fluoride versus methyl iodide. Okay, methyl fluoride, the structure is like this, and methyl iodide. So now this is the effect of electronegative atom. When we compare fluorine and iodine, we know that fluorine is more electronegative. Okay, this is more electronegative. So the de-shielding effect is greater. So if we compare the chemical value for the proton here and these three proton, okay, we know that methyl fluoride, okay, the proton in methyl fluoride, they are with higher chemical shift value. Okay, for methyl iodide is with lower chemical shift value compared to, okay, it's by comparing, okay, it's by comparing compared to the methyl fluoride, methyl iodide proton will give you lower chemical shift value because iodine is less electronegative compared to fluorine. So the de-shielding effect of iodine is also less compared to the de-shielding effect given by fluorine. Okay. So next, we move to another factor. Okay, we have seen the electronegative atom and the electron withdrawing group. Okay, that lead to de-shielding effect. Another effect is called magnetic anisotropy effect. Okay, magnetic anisotropy effect. Okay, anisotropy means non-uniform. Okay, non-uniform. So this effect is we use this effect to describe the higher chemical shift or to explain the higher chemical shift value of multiple bond proton. Okay, multiple bond proton, including the aromatic proton. Okay, aromatic proton, they are with higher chemical shift value, and also the multiple bonded proton, like the proton that attach to a carbon-carbon double bond. Okay, so for the aromatic proton, okay, for aromatic proton, under the external magnetic field, okay, the magnetic field, let's say, is in this direction. Okay, the magnetic field supply is in this direction. The aromatic compound will arrange itself to be perpendicular with the supply magnetic field. So remember that aromatic ring is a flat ring. Okay, it's planar. So under this magnetic field, you arrange itself. So you imagine that it's a flat ring, okay, and it is perpendicular to the to the external supply magnetic field. So under this arrangement, the pi electron, okay, in aromatic ring, remember you have multiple bond, you have double bond here, you have pi electron. Pi electron, they are free to move. So when the pi electron, they are perpendicular to the magnetic field, they will move, okay, they will circulate. Okay, the electron will circulate in this direction. Okay, the electron will circulate in this direction in the ring, and this circulation of electron will generate a secondary magnetic field. So besides the external supply magnetic field, there will be a secondary magnetic field generated by the circulation of electron. Okay, the circulation of electron is like this, in this direction. Okay, in this direction. This is the secondary generated secondary magnetic field generated by the movement of the electron in the ring. Okay, so you have this secondary magnetic field, okay, in this direction. So you try to imagine that you have aromatic proton. Okay, aromatic proton. They will experience greater magnetic field because, as you can see here, the external supply magnetic field is in this direction, and due to the circulation of the electron, which generate the ring current. Okay, this green color here is the ring current. Okay, and due to the secondary magnetic field, which is also in this direction, okay, so now you can see you have the supply magnetic field and the secondary magnetic field. This will make the aromatic proton, okay, the aromatic proton experience greater effective magnetic field. So similar with what you have learned just now, when the proton experience greater effective magnetic field, the precessional frequency will be higher, and this will lead to higher chemical shift value. This is why aromatic proton, they are with higher chemical shift value. Okay, it will be around 6.5 to 8 ppm compared to the aliphatic, the straight chain proton. Okay, straight chain proton, they are with lower chemical shift value. Okay, so this is also similar for the multiple bond proton. For example, this when you have carbon double bond and you have hydrogen. Okay, so when the external magnetic field, okay, external magnetic field is in this direction. Okay, you have pi bond here. Pi bond will have the electron which is free to move. So now the electron move along the bond, the double bond, and this will generate the secondary magnetic field. Okay, generate secondary magnetic field in this direction. Okay, the secondary magnetic field is in this direction. So now you see the proton, okay, it experiences greater effective magnetic field because now you have the external supply magnetic field in this direction and also this secondary magnetic field generated by the pi electron. Okay, is also in this direction. So similar with the aromatic proton, now this proton is with greater effective magnetic field, and this will lead to higher chemical shift value. So compared to the single bonded, okay, the proton in alkane, the proton that is bonded to multiple bonded carbon is with higher chemical shift value. Okay, and also this double bond and this double bond is also will give greater chemical shift value for the aldehyde hydrogen here, because now, okay, the hydrogen in the aldehyde, okay, this hydrogen will have very high chemical shift value because of two effects. You have double de-shielding effect. One is from the double bond, another one is from the electronegative oxygen. Okay, so the aldehyde proton is with very high chemical shift value. So now we have done with the chemical shift. So by looking at the value of chemical shift, okay, whether it's a small number or big number, it is very helpful for us to know the structure, okay, of the compound. So next is the integration. Okay, integration, like what I have briefly told you at the beginning of this video. Okay, for example, now you have something like this. Okay, you have three signal. The integration normally appear as a line that overlap with the signal. Okay, something looks like this. Okay, so integration is actually the area under the peak. Okay, integration is actually the area under peak, okay, under the signal, and this integration tell us about the relative number, okay, the relative number of proton that responsible for each peak, okay, responsible for each signal. So normally, if let's say it is given by a line overlapping the signal, we can measure, okay, we can measure the length of the line to find the ratio between the line. So for example, this could be from here, after you measure the length, the ratio could be 3, and this one 1, this one 2. Okay, so you know that the relative number of proton that give you this signal is 2, this signal is 1, and this signal is 3. Okay, so maybe I give you some structure. But one thing I need to remind you here is this is the relative number. Okay, it's not the absolute number. So maybe from the example it's easier for you to understand. Okay, so if let's say we look at the same example that we have seen just now, okay, the ether. So just now we have seen that this symmetry ether will give us two signal. Okay, this 6 proton give one signal, and these four protons give another signal. So you see the ratio, okay, is now 6 to 4. Okay, 6 to 4. The signal, the integration for the two signals is given by 6 proton versus 4 protons. Okay, this one for the integration you'll find 3 to 2. Okay, this is the integration. Okay, because integration is the relative number, remember, is the relative number. So if let's say you have a structure that give you two signal, and the two signals are given by 9 and 3. Okay, for example, if it is 9 and 3 protons, the integration, okay, for these two signals will be 3 to 1. Okay, you'll find it to be 3 to 1. Okay, so this is another useful information that we can get from Proton NMR, the integration. And lastly is the spin-spin coupling. Okay, spin-spin coupling, or the multiplicity of the signal. Okay, so you can see that signal, when it is with one line, it is known as singlet. When it is splitted into two fine line, okay, it is called doublet. When it is 3, then it's a triplet. When it is 4, it is a quartet. Okay, you have a 5, 6, 7. Okay, for 5 it is quintet, 6 is sextet, 7 is septet. So this multiplicity of the signals is also very, very, very important for us to solve the structure of the compound. Okay, the multiplicity or spin-spin coupling of the signal depending on these rules. Okay, this n plus 1 rules. So now remember, we are focusing on Proton NMR. For Proton NMR, the n here, the definition of n is the number of neighboring protons. Okay, the number of neighboring protons, m plus 1. So maybe we look at some example. The CH3, CH2, CH2Br. Okay, the three signals here, 1, 2, 3 signals given by 3 non-equivalent protons here, they will be with different multiplicity. So how to determine the multiplicity of the signals? Okay, we can use the n plus 1 rule. So let's look at each type of proton one by one. So for this proton, n plus 1 equal to, okay, let's determine the n. For this, we look at the neighbor carbon. Neighbor carbon is with 2 hydrogen. Okay, so you have 2 neighboring protons. So it's 2 plus 1 equal to 3. 3 is a triplet. So the signal given by this proton will be a triplet. let's look at the second one. Okay, the second one, this proton, okay, n plus 1, n is the neighboring proton. You have this as neighboring proton and also this as neighboring proton. Okay, remember neighbor can be from both sides. So now the n equal to 3 plus 2 is 5. You have in total 5 neighboring proton. 5 plus 1 equal to 6. So the signal given by this proton, okay, this proton is a septet. Okay, let's look at the last one, this one. N plus 1, n equal to 2. The neighbor proton is 2 plus 1 is 3. So you get a triplet. So the three signals that you can see on NMR, the proton NMR spectrum for this compound is 2 triplets and 1 septet. Maybe I give you another example. The CH3, CH2OH. Okay, so first maybe we try to determine the number of signals first. Okay, this 6 proton, they are the same. They'll give you one signal. This another signal. And these two give you one signal. And the OH, this another signal. So now let's determine the multiplicity of the proton, of the signal. For this 6 proton, okay, the neighbor is this. Okay, the neighboring proton is this. So n plus 1 equal to 1 plus 1 is 2, is a doublet. Okay, so for this proton, the neighboring proton is this, okay, and also this. So now you have m plus 1, it is 8 plus 1, it is 9. Okay, for 9, I'm not sure about the name for the multiplicity for 9. Okay, it's actually not very usual to have 9. Okay, so now you need to know that multiplicity for this signal will be splitted into 9 fine line. Okay, so let's look at the next one. For this proton, the neighbor proton will be 1. Okay, we don't count this as the neighbor proton for this proton, because we only consider the neighbor proton when it is attached to carbon. Now this proton, okay, is not considered as the neighbor proton because it is attached to oxygen. There is no spin-spin coupling for the hydrogen that attach to oxygen and also nitrogen. Okay, so for this proton, the multiplicity of the signal will be n plus 1, which is n is now 1. Okay, this one, 1 plus 1 equal to 2, so you have doublet. And for this, okay, so remember there is no spin-spin coupling happen through the oxygen. Okay, no coupling. So for OH proton and NH proton, it will be always a singlet. Okay, because N will be 0. 0 plus 1 equal to 1. Okay, so we look at the last example, aromatic compound. Okay, CH3, CH2. Okay, so I hope you still remember how to determine the number of signals. First, let's look at this. NH2 is a singlet, remember, for the proton that attach to nitrogen or oxygen. Okay, nitrogen or oxygen. There's no spin-spin coupling, so the N will be 0, okay? N equal to 0. The number of neighboring proton is equal to 0, so the multiplicity for this proton is a singlet. And remember, you have hydrogen here, you have hydrogen here. Okay, these two, they are the same. These two give you another signal. Okay, so the multiplicity for this will be 1 plus 1 because of the neighbor. You have one neighbor. So it's a doublet. For this one is also a doublet because also 1 plus 1. Okay, you have another two signal. One is this and another one is this. Okay, the CH2, the multiplicity for CH2 would be 3 plus 1. Okay, because the neighbor is 3. So it's a quartet. And the last one, this neighbor is 2. 2 plus 1 equal to 3 is a triplet. Okay, that's all for this video. I hope you understand all these 4 important information that you need to know for the interpretation of proton NMR spectrum. That's all. Thank you.